Okay, we're on to our unit about sequences and series, which isn't long. There's not much to this, but we will talk a lot about tests, as in what test do you perform in order to show that something is converging or diverging, right? These are the words that we're going to use 6,000 times: converges or diverges, okay? As x goes to infinity or as n goes to infinity, if we go to a value, right, a number, then it converges to that value. And if it doesn't have, what's this one say? If a sequence does not have a finite limit, then that one diverges. Okay, so these are words we're going to use a lot: converges versus diverges, and all the tests that will tell us whether it converges or diverges. Okay, so some basics. Okay, a sequence is simply a listing of numbers, right? A listing. So one follows another, follows another, follows another, and they don't always have to, but ours will have some type of a pattern to it that we're able to identify. Okay, there's a couple different types of sequences. There are these ones that are called arithmetic, right? It looks like the word arithmetic, but it's pronounced arithmetic, with the emphasis on the third syllable, arithmetic, not arithmetic, because it has a common difference. So look at from 3, right, looking at our terms. First we have 3, and then we have 8, and then we have 13, and then we have 18. So there is a plus 5 in between every one of our terms. Okay, this is called your nth term, or the formula that is used to generate any one of these terms. Okay, so these are all things that we can look for. Okay, so that equation is called your nth term, or what is the formula in order to find the nth term. So we would write a sub n equals 5n minus 2. Okay, the only things n can ever be are the numbers 1, 2, 3, 4, 5, 6, 7 to infinity. N are always positive integers that we are multiplying or adding or doing something to. Okay, like just like our subscripts. So subscript 1, a sub 1, a sub 2, a sub 3, a sub n. So the n value corresponds to a subscript, which is a term in your sequence. Right? The 5th term has a subscript of 5. The 19th term has a subscript of 19. And we would plug 19 into your equation in order to generate that 19th term. Okay? So there's a formula that we can use if we don't have, right? We just have our values or your terms, and that looks like this. The formula is a sub n equals a sub 1 plus the difference times n minus 1. So that's if we know the first term. Oftentimes we will know the first term. But if we don't know the first term, then our formula changes a little bit. This is a sub k, and this is an n minus k. Okay? So this a sub k is a term in the sequence. N and k, these are your subscripts. So this would be the 1, 2, 3, 4, 5. This would be the 11, 12, 13, 14, 15. Okay, so if in general, right, this is the term, the actual value from your sequence, and n and k are your subscript values, and d is the difference in between your terms. Okay, so arithmetic, very nice. Okay, and then we have something called geometric. A geometric sequence is one that has a common multiplier. So notice that each one of these terms, it's 5 times negative 3. Negative 15 times negative 3. 45 times negative 3. Okay, we are multiplying by negative 3. We can always find that ratio simply by doing any term divided by its previous term. Right? And if these are all common, no matter what two terms you pick, then we have a geometric sequence. So you can always find the ratio. This is called your ratio by dividing any term by its previous term. Okay? Then 5 here, this 5 in front, this would be the first term of your sequence. Notice how our first term is 5. Well, that's our first term 5 for our sequence also. Okay, so our formula for a geometric sequence is a sub 1 times our ratio raised to the n minus 1 power. Okay, that's the formula that we can use to generate any number of term from our arithmetic sequence. I mean our geometric sequence. Okay, that is if we know the first term. And if we don't know the first term, then these 1s turn into k's. Right? Some other term. Maybe we know the fourth term. Then we have a sub k, r to the n minus k. Okay, but if we know the first term, that means k is 1. And then there are other sequences that aren't arithmetic or geometric. Right? So here's some examples of those ones. Right? This one is the n squared term, right? So we have 1 squared, 2 squared, 3 squared, 4 squared, blah, 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 n squared. Okay, here's a formula of an exponential, 3 to the n plus 1. So this is 3 to the 1 plus 1, 3 squared plus 1, 3 cubed plus 1, and so on and so forth. Okay, or we could have a fairly complicated one where we have to plug n into top and bottom. Okay, so these are not arithmetic or geometric. They don't have a common multiplier or a common adder. Just so we know, right? We can be asked for all kinds of different things. So, determine whether each sequence diverges or converges. If it converges, find its limit. What is that number that we're going to go towards? Okay, and show why. Okay, so if we have a geometric, notice these are all geometric sequences because it's some ratio times the other one. Okay, when it has a ratio, then we're going to have convergence if your ratio is less than 1. So as long as that number we're multiplying by is less than 1, our sequence is going to converge. And then if it doesn't, our sequence is going to diverge. Okay, and I believe there's a formula for this. S is equal to A over 1 minus R is our formula if our geometric sequence converges. Okay, so in this case, our first thing is 3/5. Okay, so that's our A. Our first term is 3/5 over 1 minus our ratio, which is also 3/5. So now we have to do a little fractional subtractional. What is 1 minus 3/5? That would be 2/5. And instead of dividing by a fraction, I always multiply by the reciprocal. There's going to be a lot of this multiplying by the reciprocal business. What is 3/5 times 5/2? 3/2. Okay? So as this sequence gets bigger and bigger and bigger as we have more and more numbers, right, they're going to be, well, this is a sum, so adding up to 3/5. That's what it's going to converge to. So sine of n, that means that's the sine of 1, and then the sine of 2, and then the sine of 3, and the sine of 4, and the sine of 5, right? Now remember, these are now radians. We're taking the sine of a radian angle. So the sine of 1 radian, the sine of 2 radians, the sine of 3 radians, the sine of 4 radians. So thinking about sine, what are sine's maximum minimums values? 1 and -1, right? The graph of sine oscillates between +1 and then -1, right? Where this is, of course, 2 pi, which is 6.28, right? So as sine goes back and forth as n values get bigger, does sign converge to a number? Right? No, it does not converge. It diverges, so it goes from positive 1 to negative 1, so sign of n diverges. Let's look at f. 3 times 1. Remember, n equals 1. We're going to plug in 1, 2, 3, 4, 5. So if n equals 1, that's 3 times 1 plus 2, which is 3 plus 2, which is 5. And 5 times 1 minus 1 is 4. So there's your first term. What if n is 2? Then 3 times 2 is 6. 6 plus 2 is 8. 5 times 2 is 10. 10 minus 1 is 9. So we have 8 ninths. And then if n equals 3, 3 times 3 is 9. 9 plus 2 is 11. 15 minus 1 is 14. Okay, what are some other values? We were next going to have 14 over 19, and then 17 over 24, and then 20 over 29. Okay, so what I'm doing is I'm noticing the pattern. This 3 here is your common adder. So we have 5. 5 plus 3 is 8. 8 plus 3 is 11. 11 plus 3 is 14. 14 plus 3 is 17. 17 plus 3 is 20. Okay, so our numerator has a common difference of 3, and our denominator has a common difference of 5. 4 plus 5, 9 plus 5, 14 plus 5. Okay, so is this trying to get to a certain number? So what number? This, if we took the limits, right, as n goes to infinity, if we take the limit as n goes to infinity, we're getting really, really big numbers of 3n plus 2 over 5n minus 1. Okay, notice that we get infinity over infinity when we plug these in. So if we get infinity over infinity, well, that's an indeterminate form. So we can apply L'Hopital's rule, and take the derivatives. So it's still the limit as n approaches infinity of the derivative of 3n plus 2, that's 3, and of 5n minus 1, that's 5. And the limit of a constant is constant. Okay, in pre-calculus, we learned about horizontal asymptotes. The horizontal asymptote of a neutrally heavy rational function, right, which is a rational function anytime we're dividing by a variable, would be the difference of its coefficients. So 3 divided by 5 would be the pre-calculus justification because of our neutrally heavy function. Okay, let's see some values for 3 plus negative 1 to the n. Okay, if n equals 1, then that's 3 plus negative 1, which is 2. Okay, if n equals 2, that's 3 plus positive 1, which is 4. If n equals 3, that's 3 plus negative 1, which is 2. So anytime we have an odd number here, we're going to have negative 1 as the answer, and 3 minus 1 is going to be 2. So we have two values. We have the value positive 2 and the value positive 4. So does this converge to a single number? No. It either goes to 2 or it goes to 4. So 2 to 4 to 2 to 4 to 2 to 4, 2 to 4, 2 to forever and ever and ever and ever, it never approaches a single digit. Okay, without a calculator, these are kind of hard to understand. We have the natural log of 1 over 1. Well, what's the natural log of 1? That's 0, so our first term would be 0. So then our second term, natural log of 2 over 2. That's 1/2 the natural log of 2, which is natural log of 2 to the 1/2, natural log of the square root of 2. Okay? And then, if we continue on with that type of a rationale, whatever your denominator is going to be, this is going to become the root of your natural log. So the next one is natural log cube root of 3. Natural log fourth root of 4. Natural log fifth root of 5. Okay? So division means multiplication by a fraction, and by our log properties, if we're multiplying a natural log, we can bring that to be an exponent. 2 to the 1/2 power, hopefully you recognize the 1/2 power as the square root. So this is the natural log of the square root. Okay, and then it would be natural log of 3 divided by 3. And that would be the 1/3 here, and then that would be the 1/3 power, so the cube root of 3. Right, establishing this pattern, these are all going to be decimals. The question is, are they getting bigger or are they getting smaller? Well, I don't even know. But let's do what we did above and find the limit as n goes to infinity of natural log of n over n. Okay, we want infinitely large values of n. So that becomes the natural log of infinity over infinity, which is an indeterminate form. So we can take the derivative and apply L'Hopital's rule. The limit as n approaches infinity of, what's the derivative of natural log n? That's 1 over n, and the derivative of n is just 1. So the limit as n approaches infinity of 1 over n. What did we decide this was earlier? 0. Because it's 1 over a very, very large number. 1 over a very large number is 0. So this one converges. It converges to 0, which is a perfectly good thing for something to converge to. Our last one is, oh, you know what this exclamation point means? I hope you've seen this exclamation point some other time in your life. No. This means factorial. It doesn't mean that this is a very exuberant problem. Factorial means multiply by all the numbers until you get to 1. Okay, so let's see what this looks like if we were to do n plus 1 factorial. Okay, so let n equal 1. What is 1 plus 1? That's 2 factorial over 1 plus 3, which is 4 factorial. So 2 factorial means 2 times 1. 4 factorial means 4 times 3 times 2 times 1. You multiply all the numbers less than the factorial, right, the number in front. So let's see, what can we cancel out? Well, the 2 and the 2 divide nicely, the 1 and the 1 divide nicely, and our answer is 1/12. So our first term is 1/12. So let's apply that again, but now we have an n equals 2. So 2 plus 1 is 3 factorial over 3 plus 3, which is 6 factorial. So this is 3 times 2 times 1. And on the bottom we have 6 times 5 times 4 times 3 times 2 times 1. Yes, my students are smarter than me most of the time. 5 factorial. So 5 times 4 times 3 times 2 times 1. So the 3 and the 2 and the 1 all cancel out, and we get 1 over 20. Okay, so do we see a pattern here? How can we figure out what our denominator is? The numerator is always going to be 1. And what two numbers are we multiplying together? N plus 2 and n plus 1. The first two numbers we're multiplying together. So we had 3, right? 3 is 1 plus 2, and 4 is, well, that's not right, is it? N plus 3 and n plus 2. Right? So 4 is 2 more than 2, 5 is 3 more than 2, 3 is 2 more than 1, 4 is 3 more than 1. Okay, in other words, right, this is 1 over n squared plus 5n plus 6. And for very large values of n, it becomes 1 over 0. Right, which means our function does what? No, not 1 over 0. 1 over infinity, which becomes 0. So this one converges to 0. Okay, so there's going to be lots of things that we probably have never seen, lots of algebraic things that we haven't done yet, but with a little bit of simplifying, we can make mental sense of it, and it will be okay. Okay, convergence test, does it go to a single number, or does it diverge to infinity? That's the question. Okay, we'll deal more with this tomorrow.